Now I'll introduce you to the central limit theorem. The central limit theorem says that when we're drawing a sample from a population, we don't necessarily need to know the distribution of the population, but it does help. So the first part of the central limit theorem says if we take a random sample from the population that is normally distributed, the sample will also be normally distributed. So let's take a look at an example in this case. So let's say that we have a normally distributed population and we draw a sample from that population of a sample size 10, and let's see what happens there. There's our first sample and the mean of the first sample, and let's do this 1,000 times. We can see that our population is normally distributed and our sample is also normally distributed. But hopefully you notice two things, that the distribution of our population is much wider than the distribution of our sample. And the reason for this is because the distribution that we're using is no longer the standard deviation. We're actually using the standard error. Standard error is the standard deviation divided by the square root of the sample size. In this case, the sample size is 10. Now, in many cases, we don't know the distribution of the population. So part 2 of the central limit theorem says if we take a random sample of n observations from a population, whether normal or not, then when the n is sufficiently large, I'll discuss that more in a minute, the sample distribution of the mean of the sample will approximately be a normal distribution. The larger the sample size, the closer it will be to a normal distribution. So, bringing in our example once again, let's create a distribution that is not normal. So this is a uniform distribution. When we take the same sample, sample size 10, actually let's start from a sample size of 2, we can see that we grab this sample, take the mean of those two samples. Let's duplicate this. The normal distribution gives us uniform distribution gives us an approximately normal distribution for our sample. Let's increase the sample size now to 25. We can't go over 30, which we really need to be sufficiently large. But let's see the animation again. So you can see we're drawing 25 samples from this, so our sample size is 25. Then it's going to take a mean here. Let's do this 1,000 times. Now we get a distribution that's much closer to a normal distribution. So a common question is, how large does your sample size need to be? The value of n needs to be larger the more non-normal the population distribution is. In that example, the uniform distribution still gave us an approximately normal distribution. Let's take a look at an example assuming that we have something that's very unnormal or not normal. And I'm just going to create something, a distribution that is obviously not normal. If our sample size is very small, and we do this one time, let's say we do it 1,000 times, we get a distribution that's obviously not normal. I mean, we still get kind of this humped shape, but it's not a nice bell curve that we would expect in a normal distribution. Let's change that so our sample size is much larger, and let's do this again. We can see now that we get back to that normal distribution of our sample distribution, even though our population is not normal. So, for a quantitative variable, the magic number is n needs to be greater than 30. And this is quite important here. This n needs to be greater than 30, and that will just be kind of a rule of thumb that we'll use in this class. For a dichotomous variable, that means that the value is either a 0 or a 1. There's only two possible combinations. we have to use a slightly different magic number. It needs to pass the following test. So the sample size times the proportion in the population. So let's say that it were a coin toss. The proportion would be 50-50. So it would be the sample size times 0.5 needs to be greater than 5, and the sample size times 1 minus 0.5 would also need to be greater than 5. Let's take a look at a distribution that would be dichotomous. So here is a dichotomous distribution. It's either 0 or it's 32. Let's clear the lower 3. And we have about 50-50, so we can kind of think of this as the proportion of males to females. If our sample size is very small, so 2 times 0.5 would be 1, that's less than 5. If we take the distribution, we can see that we kind of get this split range. It certainly doesn't look like a normal distribution. Let's increase that to 25. So now 25 times 0.5 would be 12.5. That's greater than 5. And 25 times 1 minus 0.5 would also be 12.5. So that's greater than 5. It fits the sample size rule. Let's see this run again. Now we can see, you still have this kind of vacant area here, but we can see it much closer to a normal distribution present. So that's the central limit theorem. And the central limit theorem here is basic to the concept of statistical inference because it permits us to draw conclusions about the population based strictly on sample data without having any knowledge about the distribution of the underlying population. In fact, we're going to do everything according to normal distributions from this point on, because if we don't make the assumption of normal distributions, which the central limit theorem allows us to do, then we have to use non-parametric or non-parameter based statistics, and that would be appropriate for a more advanced course than what we're going to cover here. So the central limit theorem really allows us to know the distribution of our sample regardless of what the distribution of the population is.